gotten higher, the peak has moved, but it's the same basic curve. That was at 1800 K. And every time we raise the temperature, we get a new curve. Every time we raise the temperature, the curve goes higher and the peak shifts to higher frequencies. Therefore, in the latter part of the 19th century, physicists realized that there is some relationship between temperature and radiation. And we don't know what it is. We didn't understand radiation very well in those days, but we knew that there was some physics connecting this curve and that experiment. And we don't know what it is. Very often, this is how it goes in physics. You dream up an experiment, you make some measurements, and then you try to figure out why do these measurements come from this experiment. It's kind of backward logic, but it does happen that way. Instead of, most people think that in physics you start with a theory, you develop a formula, then you do an experiment to test the formula. That's only when everything's done. It usually works the other way around. You come up with an experiment, and then you try to figure out the physics that explains the experiment. It goes backwards. And that's exactly what we did here. People started looking at this, and they realized that, well, there's two interesting things going on. Temperature goes up, peak moves, and elevates. And so they started to do something that, oh, it's so much easier nowadays. Don't you guys have handheld calculators where you can just put in a few data points and it will curve fit for you? Oh, that is so nice. That's so luxurious. Because back then, even just a few decades ago, you literally had to start guessing equations that would fit the curve. And people who were good at it were rare. So very often it took weeks and weeks of guessing different kinds of equations before you came up with something. And that's what was happening back in the latter part of the 19th century. And we found two interesting equations. One relates to the peak. Where do you find the peak? And I'm going to call this frequency 1200 K, which of course is related to the wavelength at 1200 K. And this was the relationship that a physicist named Wilhelm Wien worked on. He said, hey, there's a unique wavelength, lambda for 1800 K. There's a unique wavelength for each temperature. Is there a relationship that tells me about it? And there is. He discovered that there is an equation which will predict exactly where the peak of any curve is related to the temperature that generated that curve. And he simply wrote down the equation. It looks like this. Lambda max times the temperature, of course in kelvins, you must measure it in kelvins, is 2.898 times 10 to the minus 3, and that's in meters times kelvins. He found out that relationship works. If you simply use this number, which by the way is very much like the number 12 when you're converting back and forth between feet and inches, this is just a conversion factor. This number is a conversion factor, then that product will always be this number. 2.898 times 10 to the minus 3. Oh, wonderful! Then what's the physics? What causes? Have no idea. Wien, Wilhelm Wien was his name. He said, I have absolutely no idea why this works. But I've done exhaustive experimentation and found out that it does work. Of course, normally you publish something like this in laboratories all over Europe. Says, oh, really? Is this really true? We're going to test it. And so for the next year, people were testing it, and it worked. It worked beautifully. Nobody could figure out why, but it worked. By the way, for your information, so, of course, the physicists are going to sit in their labs scratching their heads trying to connect these things together with the physical law. How does this product produce this number? What is the physical law? They couldn't do it with that. They just couldn't do it. The astronomers didn't care. You know why? Because all of a sudden now they have a powerful tool. All they have to do is turn their telescope towards a bright object in the sky. Choke down the image so that they're absorbing light only from that one object, perhaps to start. Measure the brightest surface color. Find out what the wavelength is of the surface of that object, and you know the surface temperature. What a powerful tool, eh? If you want to know how hot a star is, you don't have to go to the star and stick a thermometer in it and wait. All you have to do is look for the brightest surface color. That's why the astronomer said, hey, this is a wonderful law. Wien's law is a wonderful law. It will really help us. We can now measure the surface temperatures of bright objects in the sky very, very easily. Example, the surface temperature of the sun on the average is about 5,800 Kelvin. Now we got that instantly. So the astronomers, said to the physicists, once you figure out why this is true, we'll be interested to know, but for right now, this is just a tool in our toolbox. Okay, Wien's law, that's one of the tools I wanted to talk about today. The other observation was made by another group, and they were interested in what's the total energy output. Here's an object at 1200 degrees, and it's producing, well, the total energy output is the integral of this curve, isn't it? It's the total area under the curve. So if you integrate the curve from 0 to infinity, you find out what the total energy is. And of course, each time you raise the temperature, the value is going to go up dramatically. I tried to imply that just a change of 600 kelvins. Look at how much higher it's got. You can imagine the area under this curve is significantly more than the area under the 1200 curve. Two men working together, Stefan and Boltzmann, found a relationship for the brightest surface temperature, or brightest surface color and surface temperature, and the total energy output. So, the total energy output, which I'm going to put down as phi is energy per unit area, is given simply as, if it's a black object, sigma t to the fourth. By the way, this term, phi, is flux. Energy per unit time and unit square area. So that's the flux for a black object, and let me put that in black. Like a star. If it's not a black object, you have to make a little adjustment to this thing. But this is called the Stefan-Boltzmann law, which says that the energy flux, the energy per unit area, is simply equal to a constant called the Boltzmann constant, 5.67 times 10 to the minus 8, 5, 6, 7, 8. 5.67 times 10 to the minus 8. And then the units, of course, have to be in watts per meter squared, Kelvin to the fourth. So that's the Stefan-Boltzmann constant like that. And it's the same story, ladies and gentlemen. They did a lot of work, tested experiment after experiment, and this equation always works, but there's no explanation. What's the physics? We didn't know. So for right now, we have two radiation laws that seem to work. They've been tested. The only reason we know they work is because the experiments have been done and they've been tested. We do not have an explanation yet for why these two things behave the way they do. But these are the two radiation laws that we have. All right. Why does the black-body radiation curve have that shape? We didn't know. By the way, a little later, when we get around to the specific details, in the latter part of the 19th century, two men, Rayleigh and Jeans, were guessing at some classical physics to explain this curve, and they almost got it. Their guess led the brilliant Max Planck to the correct guess. And I'm actually going to show you both. I'm going to show you Rayleigh Jeans, which got us started, and Planck, who finished it off. But it took a couple of decades of serious work before we actually found the physics. So that's just a hint of preview, a hint of coming attractions, because I have here for you 2 guesses with no explanations, and I don't want you to think that that's all there is to the story. Eventually we figured it out, but I'll tell you about that in about, 2 weeks. Okay, so Raves and Jeans and then Max Planck will be our topics. Let's look at problem number 38. Let's look at a problem and talk a little bit about how you use this information to solve the problem. Here's what our problem is going to be. Imagine that I have some sort of a heating element in here, 120 watts. This produces heat at 120 watts. Then it is surrounded by 2 spherical shells, 2 metallic spherical shells. The first spherical shell is 1 meter in diameter, it's 1 meter in radius, so it's 2 meters in diameter like this. And a second shell, which is twice as big, it is 4 meters in diameter. So the first shell is a 1 meter radius, the second shell is a 2 meter radius. I showed diameter here just because it's easier. And what we would like to do is see if we can take our knowledge, especially of the radiation law here, and try to determine the temperatures of the 2 shells, which I think we call simply T1 and T2. Those are the questions. If we know a couple of things. First, these are nice metal. Secondly, there's 120 watts inside. Third, this is the key, it's all in thermodynamic equilibrium. In other words, of course, when you first turn on the heating element, temperatures are changing. We just walk away from the experiment for a little while and let everything get to thermal equilibrium. And then we're going to try to determine what temperatures T1 and T2 describe this system in equilibrium. Well, of course, an important thing is that if you're in equilibrium, everything has to eventually lose 120 watts. There has to be 120 watts leaving everything. Otherwise, you're not in thermodynamic equilibrium. If you're losing more or less than the amount generated inside, then the temperatures will either be going down or up, respectively. So let's now look at the outflux, the energy outflux at surface 1. This thing has to be losing 120 watts because it's gaining it inside. Hence, therefore, F out, the flux out, must be the area of sphere 1 sigma T1 to the 4th power. And of course, that is going to be 4 pi r squared T1 to the 4th power, like that. At the same time, from the outer shell is going to be warm. It's going to be radiating in as well as out. So there's going to be an outflux and an influx at this surface. So at the same time, F in is going to be, of course, A2 sigma T2 to the 4th power. So we'll write it down the same way, 4 pi, now r squared T2 to the 4th power, like that. And you'll notice that T2 represents the outer shell, and I use the capital R, the larger R, to represent that radius. The net heat flow out, anywhere in between the two, the net heat flow has to be equal to the power input. So F net, anywhere between these two, anywhere at this surface or arbitrarily in the middle, the net flux must be the sum of the 2 fluxes, and that is F out minus F in. F in is coming in this direction like that, coming from the outer shell like that. So, of course, that becomes what? The F out was the little r and the T1, so 4 pi r squared T1 to the 4th power minus, and this is the F in, so it's got the big R, 4 pi. Did I leave something out? I did. Sigma. Sigma. I left something out, ladies and gentlemen. If you're writing your notes, I left this
sigma out, see?